So yeah, thank you for coming to our virtual town hall on open shading language. So I thought I'd give a brief introduction to what OSL is. Open shading language, which we call OSL, is really a shading language for artists to describe materials for modern production renderers. It's integrated into many popular renderers, including the ones listed here, as well as a few proprietary production renderers that are in-house renderers that used at some movie studios. And but open shading language is also an open source project, which consists of a compiler and a runtime for both CPUs and GPUs. So OSL as the open source project consists of some of these components here. So we have OSL-C, which is our command line compiler. That's what takes the artist written source code to the shader and turns it into bytecode. This is also available as a library. We have libOSL query, which is our library for inspecting compiled shaders and runtime, figuring out what parameters they have, their default values, some of their metadata for building UIs, things like that. And then libOSL exec, which is kind of the heart of the project, which is our LLVM-based runtime for both CPU and GPU. We currently have 3 different backends, and this covers different use cases. So we have the oldest one, which is our 1 point at a time shading backend that covers x86 and ARM CPUs. That lets you shade, execute the shader for 1 point at a time. And then we have a new batched backend that runs on x86 and wide SIMD instructions. So we have x512, and that lets you shade multiple points at once. And this is used, for example, in Pixar's render, which is designed to take advantage of this. And we also have a backend for CUDA kernels. And so in this mode, OSL will generate PTX for you that you can then feed into a CUDA-enabled renderer to do shading. On top of the core libraries, we also have a few testing applications, including test shade. This is really a small example that just shades a grid of points to produce an image. We have test render, which is our minimalist path tracer, and it's really meant to just give you an example of how you could integrate OSL into your own renderer. And OSL Toy, which is kind of inspired by Shader Toy. It's a small Qt UE application for shader prototyping. It basically does the same thing as test shade. It just has a small UI in front of it. So what are some differences about OSL compared to other shading languages? So the way you can write shaders individually, but you can also assemble them into networks. And these networks are evaluated lazily by the runtime. That means that any unused sections of the material are not evaluated. And this is important for performance for very large and complicated shader networks. Another useful property that our runtime has is that it optimizes the entire graph of the material. It doesn't look at shaders individually. It considers how they're plugged together. So that means that we can optimize across nodes, even nodes that have been written by different shader writers, and consider really the material as a whole. And this is designed to scale to really very large production shaders. And we'll hear about this a little bit later in the presentation. Shaders that can have lots of features, but once they're plugged in together, all those features may not be used all at once, and the optimizer can remove a lot of instructions to make them run fast at runtime. Another unique feature of OSL is its use of automatic differentiation. This is the strategy for filtering and bump mapping. Basically, anytime you need to capture the derivative of something in a shader, we handle this through automatic differentiation, and the compiler and runtime keep track of the minimal set of instructions to add to make this happen. And this is basically just more accurate and more efficient than doing finite differences, which is kind of the other solution to this problem. And finally, shaders in OSL are a little bit different in that they don't return colors. They return what we call closures. So the renderer decides how it's going to handle the lighting and all that. And you the thing you hand back is actually just a description of the material properties through these objects that we call closures. And you can achieve very complicated layering just by combining these closures into closure trees. The other material related project that is in the Academy Software Foundation is Material X. And sometimes people ask us, how is OSL related to Material X? Are these, how are the projects working together? So really, Material X is kind of a higher level project, and it's aimed at material interchange. And so the Material X library can actually convert material graphs into OSL, but it can also generate other shading languages as well, such as GLSL and so on. But the key is that really both projects are working together to establish standards. So for example, Material X adopted OSL's definition of noise functions. And then on the other side, OSL adopted Material X's definition of BSDFs and EDFs and layering operators as their standard set of closures. And we announced that last year. So what's new in OSL this year? We did a total of 8 point releases for OSL 1.12, which is our current stable version. It includes a bunch of bug fixes, of course, a number of build improvements. So we added support for LLVM 15. Optics is no longer a dependency for the CUDA backend. That gives you a little bit more flexibility. It simplifies the build process. We've also made a number of improvements to test render, which is now to support Material X, which now uses test render kind of in their unit testing framework. And of course, we've also been working towards the next stable release, which will be OSL 1.13, and we're planning an official release of this in September. So I'll include improvements to the PTX backend for CUDA optics. We have a new optimized path for input and output attributes, which has been a collaboration with Animal Logic, and also some improvements to the reparameter API for interactive edits. As I mentioned earlier, the OSL runtime tries to optimize entire shading networks, taking full advantage of what parameters it thinks are constants and trying to propagate that throughout the code. But in an interactive setting, you may want to change some of the parameters after the fact. And this API lets you flag certain parameters as being editable, so the runtime optimization will leave them alone and let you change them after the fact. So that covers kind of the main changes that went in this year. And concludes actually the first part of this session. I just gave you kind of the brief intro and project status. We're going to hear from Mitch next, who's going to give us a lightning intro to writing OSL shaders. And after that, we'll have a presentation from Chris Hallmuth at Imageworks, who's going to talk about their experience integrating the OSL GPU backend into their production renderer. We'll also hear from Alex Conti at Imageworks, who will talk about the design of using imager shaders in OSL and some just their experience with that process. And then Alex Wells from Intel is going to talk a little bit about bringing OSL to SpurV. So this will be a new backend joining the 3 other existing ones. And he's going to talk about the design of that and some of the changes that will be required for the API. And then Larry will close us out with a kind of roadmap for the future and what we'll be working on in the coming year. So with that, I'm going to hand it over to Mitch. So I'll stop sharing and let Mitch share his screen.
Okay, let's see here. That screen share. And there we go. Okay, so hi, as Chris said, I'm Mitch Prater.
Mitch, we're seeing the speaker notes, not the slides. I mean, we're seeing the whole
wrong screen being shared. Okay, hold on here. Let's try that again.
Don't worry, I'll probably make that same mistake myself.
Okay, where did the window go now? Great. Stop share. That's what I want. Okay, share screen. This is confusing. Which it should be that one, right? Is that one working now? Or hold on? Are you now seeing it?
Yes.
Yep,
That's
good.
Good. Okay. And now I have gone off my first slide. So there we go. Anyway, all right. So there's a course I'm presenting. It's a graph. I gave one last year. It's about writing shaders in OSL. I've updated it a bit for this year. So what I'm going to do now is just go through that extremely quickly to give you a quick taste of what that course will contain. So as obviously I already know, OSL is a project of the Academy Software Foundation. GitHub is located there. I don't know if I need to go over this. Shaders, for if there's anybody on this call who doesn't know what shading is and we're just curious about OSL, it's simply a shading language is just a programming language that's specifically designed for writing shaders. So OSL is very C-like. In fact, when I edit OSL, I just equate a .osl file with a C file in my code editor, and I get all the nice variable highlighting and syntax and whatnot. I thought I'd mention some open source renderers that use OSL. So there's Appleseed. That's a fully open source rendering package. Cycles is developed by the Blender project. Blender is a content creation application. Both Blender and Cycles are fully open source. And there's some commercial rendering systems. RenderMan is one. You can use it freely for non-commercial purposes. There's 3Delight. Actually, 3Delight is the first license is free. You can use it for commercial purposes even, but it also has a flexible cloud rendering ecosystem, so you can purchase additional rendering processing as needed. And Arnold is Autodesk's rendering software. It has a 30-day trial period. You can use it for 30 days without cost. And Octane also supports OSL shaders. Octane is a GPU-only renderer, so you'll need an NVIDIA card or something. It supports CUDA, and it has free and trial versions. So the outline of the course is divided into 4 major sections. First, I go over OSL itself. In the course, I'm covering pattern generation only, not any of the closure functionality. So patterns are a big part of shading and authoring shaders. So there's plenty to cover in that. Next, I'll go over some OSL examples illustrating some of the more fundamental shading tasks. And then I'll go over some interface design and metadata that you can attach to parameters to control the user interface that's presented to the end user for your shader. And then I'll talk about some development and deployment issues, just organizing your source code in a build system and debugging shaders and that sort of thing. So the crux of pattern shading is creating variation over the surface of an object. And to do that, we need to have information about the surface itself. So OSL has some predefined, or they're called global variables. These contain values that change depending on exactly what point on the surface is being shaded by the renderer. So here's our first shader. It's named global P. It has an output color called color P. And in the body of the shader, in order to, it's accessing the global variable P. So accessing global variables in your shader, you just use them. You don't have to declare them or anything. They're just part of the language. P is the 3-dimensional location on the surface of the object that's currently being shaded. P and the other capitalized global variables are initially in what's called common space, which is the coordinate system that the renderer is using. So in order to put them into a known space that you could use for shading, you have to use the OSL transform function. Here we're transforming it into the object space. And then we're using another OSL function called floor to create a sawtooth pattern by subtracting the integer portion of P object from itself. In this case, floor operates on each of the X, Y, and Z components individually. So you get a red sawtooth in X and a green one in Y and a blue one in Z, which results in the color you see here. And we're also automatically typecasting this from a point to a color and assigning that to the color P output variable. N and NG are surface normals. Normals are unit-like vectors that describe the surface's orientation. N is typically called the shading normal, and NG is the geometric surface normal. If you are using displacement on the surface, like P, these will also be changed to reflect those displacement changes. I is useful. Sometimes it's called the I vector, as in your observer or I, and in this case, it's the camera, from the eye to the surface. So if it was actually, you had a reflective surface and this was coming from a secondary ray, it would be from that location toward the shaded object. This is using two other OSL functions, normalize and abs, to produce positive values that range between 0 and 1 and assigning them to color I output. U and V come from the geometry itself and its inherent surface parameterization. Since this is a subdiv teapot, we're seeing each little subdiv face set has its own UV coordinate system. And so let's move on. So coordinate systems, mentioned those briefly. Here are some of them that are available in OSL. So we've seen this code before. I'm just going to use this to illustrate the what these spaces do. So object space sticks with the objects. Every object has its own object space. World space is the scene coordinate system. So it stays rigid with the scene itself. And so as you move the camera around or the objects in it, they'll swim through world space. Skip camera screen space is sort of related to camera space. It's plus and minus 1. Anyways, the camera image plane, suffice it to say. NDC is the image output rectangle, goes from 0, 0 to 1 to 1. And then in a DCC, you can create your own coordinate systems. So those are handy as well. So let's go code examples. All right, so lots of different types. They're just going to start off with some simple thing here just to convert float values to a color. Right, and so when you write a shader and compile it and then use it in a DCC, it'll look something like this. You'll have a node that represents your shader that you wrote and an interface panel that lets you access the parameters. So this one does the opposite, converting from a color to float values. So in this, you'll notice we're using struct-like notation on the color parameter to access its individual components. OSL lets you use this kind of notation or array subscript notation to access the components of a 3-tuple variable type. That's a color, a point, a vector, or a normal. You'll also note this node has more than one output parameter. Fact is, a shader or a pattern shader doesn't really need any input parameters at all, but it has to have at least one output parameter. Otherwise, it's not going to be connectable to anything, so it wouldn't be of any use. So more complex conversions. This is, oops, sorry, I didn't mean to skip it, but yeah, it's basically the metallic and let me go back one. This, yeah, it's a base color and metallic conversion. Simple, been around forever, and that's what it looks like. This one's a bit more complex. We're going to convert specular face and edge colors to physical colors. And I can see I'm getting behind here, so I'm going to start going through these very quickly so I can keep into my 10-minute time allotment. So colors and spaces. So the course shows how to create 3D spaces in a node that lets you do interesting things like make the space stick to an object, but actually be scaled uniformly throughout the scene using a different space. And that's controlled by a parameter. The course will cover texture access, and then of course procedural patterns are the big category. Again, we've seen spatial conversion, so I'm not going to belabor those. Let's move on. There's noise, various kinds. There's cell noise, there's Perlin noise, there's simplex noise, Gabor noise, and then we can use, well, fractals are a technique of adding patterns to themselves to create self-similar patterns. So here's their course covers a fractal using noise and let's do erosion. Here's a simplex noise and cell noise fractal. Fractals can be created from any pattern. Covers cellular patterns. And let's see, what else? Okay, yeah, sorts of things you can do with cellular. Warping, yeah, another simple technique for distorting the space that you use to create a pattern. And then, of course, there's ray tracing for doing occlusion, things like that. And I'm over my time limit. So I'm going to flip all the cards, as they say. There's a great deal more in the course, but that's all I've got time for. So so there will be a GitHub containing the supplementary materials for the course. It's not available quite yet, but anyway. And then Leica has other open source projects along with last year's course notes and things and supplementary materials. So, all right, thanks. Hope to see you at SIGGRAPH. Escape that and stop share.
All right. Thank you, Mitch. And I'll bring back my set of slides so I can share. Yeah, there we go. So I can share the following talks. So we first have Chris Hallmuth from Imageworks, and he's going to talk. He recorded a talk about OSL GPU in production at Imageworks. So I'll play the video.
Hi, my name is Chris Hallmuth. I'm a rendering engineer at Sony Imageworks, and today I'm going to talk about our experience bringing OSL GPU to our in-house Arnold renderer. I'll cover two things. First, a quick story about an interesting performance bottleneck we hit while porting our OSL implementation to Arnold GPU, and then a recap of some improvements we've made to OSL's GPU implementation over the last year that you can benefit from today. So last fall, we rendered our first OSL production assets on GPU. As we worked our way up from simple to more complex assets, most of the work was expanding our render services features to match the CPU's existing behavior. But on the side, we were also noticing that memory requirements were going much faster than we expected, and occasionally we even hit assets where OSL's memory footprint pushed us over the limits of the device. We added some instrumentation to OSL and learned that our memory problems were being caused by a few big shaders with massive group data buffers. The average shader in a scene might not have caught our attention, but outliers were hitting 50 or 60,000 bytes. A few shaders even went over 100,000 bytes. On CPU, 100K per thread certainly isn't great, but it's also not the end of the world. But with 200,000 threads on GPU, that would be 20 gigabytes of memory just for group data. Not to mention that if you're actually reading and writing that much during shading, then your path tracer is probably going really slow. So our problem was group data, but what is group data exactly? Group data is a per shader group buffer that is usually abstracted away on CPU, so not everyone may be familiar with it. But on GPU, it's managed by the renderer, and you explicitly pass it in. It's a single car array that acts as a container for global variables during a shader's execution. It's split into 3 segments: bit flags that track whether a layer has been run, cached user data lookups, and connected parameters for all your layers. On our shaders, connected parameters are well over 90% of the memory budget, so we focused there. We had guesses about where the overhead was coming from, particularly layers that merged or combined entire materials. But before we followed our intuition, we started logging and analyzing group data costs at a per layer granularity, and of course our guesses were wrong. We found that most of our group data costs were coming from a single struct called stdata, which was connected in most of our texture-related nodes. Texture samples in our shaders are often generated in a separate layer from the one doing the texture read, which means samples get passed around as parameters and live in group data. We use an array of samples for better filtering quality, and stdata is the owner of that array. So far, nothing unusual except that the array was defined with a length of 54. So at 12 bytes a sample, a layer with stdata input and output connections was already over 1,000 bytes, single-handedly making it our GPU bottleneck. We got really lucky that the array only needed to be that long for a small subset of displacement shaders, so our shading team was able to quickly rewire things to always use a much smaller array of length 6 during regular shading. It seemed reasonable to assume that reducing that array would have a nice performance benefit, but we didn't really know how much to expect. It turned out that with just that one fix, our lighter assets rendered up to 2 times faster, And our heavier assets got up to 4 times faster because now we could fit them on the stack. And our group data buffer sizes dropped anywhere from 1/2 to 2/3, relieving a lot of memory pressure. Excited by that improvement, we asked our shader team to try to chip away at our group data usage. And on top of all this, they've delivered a stream of 10% improvements since then. And also our optics module compilation times have dropped by half with all these improvements. So that's a nice side benefit. So takeaways. When we benchmarked that improvement on CPU, we didn't really see a huge benefit. The lesson I've taken from this is that your status quo on CPU might just be a huge bottleneck on GPU. So I encourage you to dive in and find out. And if you need a place to start, we exposed the LLVM group data size attribute on shader groups so that you can check yourself. Additionally, we've made some other improvements on the GPU side that everyone can benefit from. The biggest is the new reparameter mode that lets users edit shader parameters without recompilation for instant rendering feedback. We've also reduced the GPU's code gen footprint quite a bit by removing a bunch of run layer checks when reading parameters connected to layers that are guaranteed to already have run. This also removes a bunch of group data reads. We added a new GPU API where OSL owns the group data buffer instead of the renderer, which is simpler and lets optics calculate tighter stack bounds. It also removes the need for separate init and entry optics callables. And finally, we've plugged a bunch of holes where PTX was being generated non-deterministically. So now re-renders will always hit the optics cache instead of having random module recompilation. And there's more in the works. Hopefully we can reduce the group data size from the OSL side too, not just from the renderer side. And one last thing, in the middle of all this, we started visualizing some of our shader networks to get an idea of what we were up against. I thought I would share a couple, starting small and working up to some of our massive shaders to give an idea for how a 100K group data buffer came into being in the first place. So first, some of our shaders truly are simple, like this shadow shader that just reads from an existence map, or this simple material. But these aren't really representative of our median or typical shader, which is closer to this network blending together a couple of materials. And now on the heavier side, I have no idea what the rest of these do, but the scale is kind of incredible, and I love that we're able to run these on GPU. They don't really even come close to fitting on a slide anymore. But if you trust me that this is actually a shader network, if you zoom in far enough, maybe the 100K number starts to make a little more sense. And that's it for me. Thank you.
Okay, well, that was Chris Hallmuth from Imageworks, and now we have another presentation right behind from his colleague Alex Conti, who recorded a presentation about imager shaders in OSL. And I'll take that video next.
Hello everybody, I'm Alex Conti from Imageworks. I'm gonna be talking about imagers. Imagers is another made-up word. The idea came up in the context of non-photoreal rendering. After Spider-Verse, the first Spider-Verse, we got into this new project, the Missions versus the Machines, and we wanted to go one step beyond. This time we wanted more flexibility, we wanted better tools, and we thought, what if we run an OSL process in the render after all the rendering, the 3D render has finished, so we can do tweaking of the image in very different crazy ways, like doing contours based on the lighting, hatching, and whatnot. But we wanted to skip the process where we write a ton of data to disk to then use in Nuke or any other tool to do the compositing. That was the main motivation. So, okay, what is an imager? Well, an imager is just an OSL shader. It's just that instead of shading a surface, we're going to be shading an image. And the idea is that you have this piece of software, this program, little program, the shader, and has a number of inputs. In this case, the inputs are render buffers from the render. That could be the beauty image, it could be masks, whatever output the render can produce in the form of pixels. It's an input to this OSL shader or imager that then writes the result to a different buffer. That's the main idea. To do so, we have to redefine what the shader globals are. So we made this decision, but any other sensible approach would work as well. We chose to define P as the origin of the camera, and the I vector would be the ray direction, and then we would define UV coordinates. The texture coordinates are actually in the image plane from 0 to 1. So the OSL imager knows exactly what pixel of the resulting buffer is going to be computing. And how do we compute this? Well, these inputs to the imager, these buffers, can be any AOVs. We're going to be reading those from the render, and we thought of leveraging the texture code. The trick is that we create fake textures in the image cache of OpenImage.io that actually have the pixels of the buffers that the render produces, and we use this automatic bit mapping on those. So when the OSL imager makes a call to the texture, it's actually reading stuff from the render, stuff that the render has produced in a buffer. And you can do, of course, arbitrary blur using the standard derivatives or any other controls that would normally work in an OSL shader. The derivatives, things like that, they are all obeyed, so you have a lot of freedom, you have a lot of flexibility to access any AOBs in any position you want. You are not bound to access exactly the position, the pixel in of the resulting buffer. So another idea is that the images can be chained. You have, in this case, two images. The first one takes a couple of AOBs and produces another buffer, and this buffer will be the input to another imager that will do whatever operation and produce another output. So the idea is that the render keeps track of the dependencies of the images. It's going to scan your graph, your network of images, and go for the ones that have no dependencies, execute them, and then keep going until all the images have run. So at this point, the first question is, aren't you reinventing Nuke? Yes, a little bit, but why? Well, like I said in the beginning, the first motivation was to avoid writing stuff to disk. These imagers read from the buffers in memory without having to store them in files. And also, it makes sense to have a live session where you're tweaking surface shaders and render settings, and at the same time you would tweak the imagers and see the result live. I mean, with all the effects, you would look at the final result without switching DCCs at all. And also the other motivation was that, well, using GetAttribute, you can access any render internals from the OSL imager, so that gives you a lot of potential to do things beyond what a regular Nuke session allows you to do. And of course, there's other appealing things like reusing our tools for shading network design that we use normally for the rest of the process. And of course, it's OSL, so it's your favorite language applied to this image compositing. That is a great plan. What can possibly go wrong? Well, we didn't write the tools for chaining images with different outputs and that graph. So that led to monolithic design where everything was developed on a single shading group, a whole imager, monolithic imager. That was slow. The other problem is that OSL has a limitation. A layer will only run once, and on the same shader globals as all the other layers. That also led to monolithic design inside of the layer that would do all the kernel application itself without any graph where you could make sense of what was going on. And also the problem is that in the end, the comp artists still want to tweak the result. So we ended up writing data to disk anyway. What do we do now? Port OSL to Nuke? Well, we tried. So these are the lessons that we learned the hard way. Comp artists like to work in Nuke. Should we try to replace Blink script with OSL, or should we rather put the render process in Nuke with a header delegate or something like that? But the tool was available for quickly prototyping stuff. It ran in Katana. You could tweak the render and the shaders, and then at the same time tweak the images and quickly see the nice result of it. And the other lesson that we learned is that you need a good GUI to make these things friendly for the artists and efficient in the end. And that is one of the things that we could have done better. There is this interesting idea for OSL having a built-in layer in the language that would take an arbitrary layer, use it as a kernel, and execute it on a window of shader globals to then collect the results in an array or apply some reduced operation that would have improved greatly the problem of the monolithic design that we end up with. Also, of course, having a better or an actual imager output pipeline editor would have made things much better for the artists using this tool. By the way, back in those days, we didn't have OSL on GPU, so things were slow, but now we do, and things can be much faster than we got. The useful takeaway ideas is basically these three, that reading render buffers using texture calls was very useful and powerful, and we should explore it further. Also, having access to render internals via getAttribute is a very good source of information for doing this type of non-photoreal rendering. And also, there's room for improvement. Probably you can improve the shader globals. You can reconstruct the hit point from the buffers using the closest hit and maybe have the point, actual point and normal of the surface. And the idea that you don't need to switch DCCs. You do editing, you do tweaking the render and editing the surface shaders in the same place where you tweak the imagers. And that is all I have. So thank you for listening. Let's hear if you have any questions.
Okay, so that concludes Alex Conti's presentation, and now I'd like to hand it over to Alex Wells from Intel, who's going to talk about bringing OSL to SpurV. So I'll stop the screen share, and Alex, if you want to share your screen, it's your turn.
Sure, thank you, Chris. Is this visible?
Yep, looks good.
Awesome. All right, so I'll just jump into it here, in that we're working on bringing SpurV to OSL. SpurV is a standard portable intermediate representation that could be lowered to multiple devices. Now there exists a LMVM to SpurV translator, but part of the trick is getting everything into LLVM to hand off. Now, our particular case, we're interested in running OSL on the Intel family of GPUs. The Z high performance graphics microarchitecture is used in several of our products now, our data center GPUs, discrete cards, and integrated graphics. And if we did have some SpurV, we could go through the Intel One API level 0 interface to generate Z-ISO, which can run on those devices. So how do we get there? So one of the first things is separating responsibilities. Currently, the OSL runtime, it builds the shader networks and it can be used to execute them. And one of the things we want to do for this is have the OSL runtime not actually execute it, but just produce a representation of the shader network that then could be extracted as SpurV by going through the translator. And a renderer could hand that off to the one API level 0 and run it on the devices. So how do we get there? So we really need a lot of the interfaces to change to allow the same OSL library code and the same renderer code to be used for both CPUs and multiple GPUs. And along with that, as shown on the previous slide, kind of separating the execution from building the shading networks and compiling them. So creating separate CPU host runners and GPU runners to work more in a kernel launch style rather than just shading 1 pixel per call, shading tens, hundreds, or thousands of them. And the main interface for a renderer to interact with the shading system currently is this virtual render services class. And we're proposing splitting that up into something more like a compiler services versus stuff that's used at execution time. And again, the big challenge is getting all the different sources, getting everything into this LLVM module that we can then translate to SpurV. There's stuff on the host side in the renderer, there's stuff on the host side from the shading system, there's stuff on the host side for the OSL library, there's data coming from the renderer in the form of shader globals, how do we adapt to a kernel? So we've got all these different things to deal with. So we'll start with the render services. So to transition those to work better on a device, moving from a virtual function based to just a free function based. And so rather than trying to call a virtual function that exists only in the host, if free functions were provided that we could put into the bit code, then those could be integrated and called from the library functions. So here we just see kind of a straight translation from object-based to free functions, but that means we need a place for the renderer state to live. And there already was a render state, but this kind of makes it a little more formal, where a renderer would put whatever it needs into its render state, have that exist on the device, and that would flow through the kernel execution such that when their render service executes, they can extract their render state to get any data they want. And a big change here again is instead of the render services just being compiled as part of the renderer, that we need that LLVM bitcode representation of them. So a renderer would have to define its implementation and compile it through the Clang toolchain to get a LLVM bitcode that it could then hand off to the shading system. And kind of the big deal here is OSL is already producing the shader in LLVM IR, but now it would be combining it along with OSL library bitcode along with the renderer's free function bitcode. It'll have that all together to fully optimize. So we'll be able to do full inlining and a lot of other optimizations with compile time constants, dead code elimination that it wouldn't be possible previously. Another problem we run into this is strings. There's currently a system of unique strings in use, and those addresses are only valid on a host. We can't really create new strings on the fly on the device. So a solution here was to replace those use strings with hash codes that are identical on the host and the device, as well as those hash codes can be generated at compile time, const expression from string literals. Another problem is the shader globals. So how do we get this information about the shade into the kernel that's running? So rather than having a structure that's handed off, we are proposing adding a free function to populate shader globals. So again, renderer probably already has all the state information it needs, so its implementation can just access it, drill down into its internal representation, and then call some OSL setters on the current execution context to set those values. So this would be called once per sample, but again, it's all bitcode and hopefully will all be in line. Then later in library functions, when it wants to access those shader globals, it can just retrieve them from the execution context. Another problem is shading system state. So the shading system currently has several items that a shader network might need while it's executing, like the color system, current attribute values, but maybe not everything, just some things. So we're introducing this shading state uniform structure that only contains the data needed by these OSL library functions to execute. So a renderer would ask the OSL runtime to populate one of these, transfer it to the device, and then pass the pointer in with the kernel launch when it's running the shader. And now all those questions can be answered rather than trying to interrogate a host side object. Another big problem was reporting errors, warnings, and messages. Those are all currently implemented through a host side shading context. So a solution here was to add new render service free functions to handle reporting errors and warnings. That just makes it the renderer's problem to deal with, which isn't very nice. So we've provided we're providing a journal buffer implementation. It's kind of a complex slide, but we can run through it real quick. The renderer would initialize a journal buffer on the device side and let its render state hold on to a pointer to it, and then launch its kernel. While the kernel's running, if it ends up needing to report errors, warnings, or messages, those would go to its render service free functions, who would then access that journal buffer and record the information. So we're not actually doing any formatting, we're just recording everything that would be needed later. After the kernel's done running, we can transfer that journal buffer back to the host side, where it can be processed by a journal reader, where it'll decode and do all the formatting that was requested into strings, and then call out to a journal reporter, which can then actually send it to standard out or write it to a file or whatever a renderer chose to do. Other things we're looking at is overhead. An existing render service call like get attribute here. Current implementations might use spaghetti code, map lookups, or even function pointers. And even though we could make a free function version of this, all those things may not translate very well into bitcode or running on the device. So we're introducing a new concept here called a attribute getter spec. And the idea here is to move all those lookups and complicated code to shader compile time. And the way this works is this new function is called build attribute getter spec during shader compilation time, and that lets a renderer actually specify any arbitrary function to be called along with arguments to be passed. So how would this actually look in use? So let's say a renderer actually wanted to do index-based lookup of attributes. So perhaps the render state has an array of objects, which those objects have an array of attribute values broken down by type. They might want to have a getter function that looks like this. It just takes the execution context and then an integer for the object index and an integer for the attribute index, and then we'll supply the result. So it just drills down to its render state, accesses its array of objects, and then access that array of floats to get the result out. But we need the OSL code generator to actually call these. And that's what this attribute getter spec lets you do. In this case, this is called at compile time. It actually does the lookups at compile time, not runtime, to get these indices back. And it's specifying the name of the function to be called and the parameters. Now, the cool part is these parameters will be, the indices will actually be generated as compile time constants. So when that all ends up into that mega LLVM module, inlining constants folding should make it super efficient. And this same approach could be used for several other interfaces to improve things. So current status of this, the bitcode support is underway. A lot of it's upstream or waiting in pull requests or actively under development. There are some things requiring future designs, such as closure management, set and get message, which might be deprecated. There are features that could be added with no default device implementation, like point cloud and texturing. And there are certain features that are either need to be constant folded in your shader by the time it executes, or would only work on the CPU, such as dictionary and string manipulations, such as format. our path forward on this is to complete this bitcode support, then add the LLVM to SpurV translator, and add a level 0 runner for the Intel GPU family. Just want to acknowledge real quickly co-contributors on this, and special thanks to the entire OSL technical steering committee on this.
Right, very good. Thank you so much, Alex. And I think that just leaves you, Larry.
Yeah, okay, I've got
Present our closing words.
a couple minutes to wrap this all up. Let me see if I can get a screen share going. This is so hard because things cover my screen. Okay, can you see that slide?
Yeah, that's good.
Yeah. Awesome. Great. So, so I just wanted to talk briefly about what's coming, in particular over the coming year, and what the implementers have in mind on our, at least on our wish list. We'll see what we can get to. So, so one thing, of course, is, as Alex was explaining, there's a big overhaul in how the back end works. Which is largely being driven by the work of him and Stina and the Etymologic team. These changes are going to affect not just the Intel backends, but I think this is going to overhaul how all of the backends work. There are a number of organizational and optimization results that fall out of it that we think is really exciting. It should solve a number of the performance bottlenecks that have built up over the years. And of course, we intend to continue improving the other backends, and at Imageworks and elsewhere, the work on the optics CUDA side is continuing. Another area that we would like to do some more work is infrastructure. You know, from the sort of not especially exciting but got to get done category of LLVM cranks out new versions maybe a couple of times a year, and they're not shy about breaking compatibility. And we're at one of those junctures where we actually can't use the very latest LLVM 16 already, and 17 is coming down the pike. And so there are some changes that we need to make on our end to adapt to changes on the LLVM side. But also our collaboration with MaterialX continues. They have new things coming that we want to keep up with. And a number of users are using our test render program, which was originally just meant for our unit tests, but they're using it for all sorts of interesting tests. And so I think there is a desire to beef that up to be a little bit, it's never going to be a real, serious renderer, but maybe a little bit less of an extremely stripped down toy brings additional testing cases that would be really helpful. Our documentation, I'm very proud of the language spec itself, but our documentation situation is kind of embarrassing in terms of like the missing guide that you need really to integrate it well into a renderer, and other technical details like that. And I think I really applaud Mitch's work to get the SIGGRAPH course going about actually writing shaders. Because right now we're a little bit light on that, and I think there's all sorts of interesting directions that we could go with that as well. And I would like to see us bring some of the back end work that we have been really dominating the last couple of years to a close as those back ends become more mature, and pivot back to some things that we've been ignoring lately, where like our use of OSL has pointed us in directions where we want the language itself to improve from the shader writer's experience. And we have a growing number of those suggestions that we would really like to do. And I think it's partly just a bandwidth thing on our part. And speaking of which, we're always looking for people to get involved with the project. It's open source. We invite collaborations. An opportunity that is coming up that the ASWF is trying to organize is the second week of October. We're trying to have this thing that we call the Dev Day, which is sort of a one-day, we don't like to call it a hackathon, but we'll call it a devathon, where we want to recruit new people to these projects to try things and peel off, good small projects to try. And so from the from the project side, we want to identify tasks that can be done in a day or so by relatively new members to get their feet wet. And also, all of you are at companies, and so I urge you to look at this as an opportunity to find the juniors in your departments who you think would be great open source contributors, but maybe haven't taken that step. And not just with OSL, but all of the projects. Like, look for places where you can give them that day to actually build some more expertise in how to contribute to making these projects better that all of our companies depend on. So with that, we have it. I don't know if we have maybe a minute left, but we'll take Q&A until they boot us off. But while that's going, I just wanted you to take note of a few other town halls, DigiPro and SIGGRAPH activities that are OSL related or adjacent enough that you should really check them out. So thanks for your attention. And if there are any questions, maybe we could squeeze them in.
Yeah, thank you all so much. We can leave the Zoom on for a few more minutes. And if anyone has questions, feel free to put them in the Q&A box or in the chat. We can also just open it up for some discussion.
Yeah.
I just want to mention that
also
the time you have for the course at SIGGRAPH is wrong.
Oh, no, I'm sorry.
It's from 2 to 3:30.
Okay, thanks for the correction.
But it will be recorded, so, you know, whatever.
I could have just screwed that up when I was typing, but Mitch, maybe check the SIGGRAPH listing, because I don't know, I feel like I got that time from somewhere.
I'll double check.
Okay. And apologies if that was just my mistake. I would like to say also, for anyone who's listening to this now or maybe later on the recording, we have a Slack channel on the ASWF Slack. We have a mail list, and we have every second week open Zoom meetings for the technical steering committee. Any of those are open for people to participate in. It's an approachable group. Always feel free to drop in on any of those channels if you have questions or want to get involved with the project.
Yeah, from the SIGGRAPH website, it says 2 to 3:30. So
okay, sorry.
All right, anybody have any questions? I'm Larry, I'm going to take you off of Spotlight.
Okay, great.
Ooh, we do have a question from Alex. Has there been any investigation into implementing closures as OSL code yet?
No. Right, so the original idea was that the closures would largely be in the hands of the renderer, and we did say in the beginning that maybe as a later stage we would make it so that you could author the closures themselves in OSL, and we never quite got there. And in fact, we're even in a state where some of the renderers support closures and some of them don't. So yeah, I mean, I think that's an interesting avenue to take it. Like in the beginning, we could say that, like at Imageworks, for example, the first few years, we probably went through 6 or 7 different ideas of how closures should be implemented on the inside. And we were kind of thankful that we didn't put a spec out there for how to do them in OSL, because it was changing all the time. But it's been stable for a while now. So it might be at a state where it's, you know, everybody sort of agrees how it should work and what it should do. And we could think about that, but we haven't, it isn't at that point right now, like nobody's implemented it. But if somebody wanted to come to the project and try to craft a proposal for how one could author closures outside of the renderer supplying it, I think that is something we would love to hear.
Yeah, just to add to what Larry was saying, I think one of the challenges with writing closures in OSL is we're using closures sometimes to be more than just BSDFs. So they can be BSS RDFs to represent subsurface scattering or volume distribution functions. So finding a common way to describe that in OSL has been challenging. So yeah, we definitely welcome any ideas that people have on this topic. Like, it would be cool to be able to do this, but we're not quite sure the best way to do it yet.
Well, I think we can probably wrap up. Thank you guys so much, especially thank you to Gritz for leading the presentation. And we hope to see some of you again, either in person or virtually during some of the upcoming events in the next few weeks.
Thanks, everyone.
Thanks, everyone. Bye-bye.